this will be 39 times 48.5 squared over 40 squared. 39 times 48.5 squared over 40 squared. Thomas, why earlier you didn't square it, now you square it? Well, because earlier the number given to me were variance, population variance, and sample variance. Right now, what's given to me are population standard deviation 40 from the null hypothesis, the constant of the null hypothesis, okay, and population standard sample standard deviation. Those are the tools given to me. Then p-value it's a chi-squared distribution. And this is 57.33609. So p-value is chi-squared CDF 57.33609 P9939. Right, that's the degree of freedom. Then I use my calculator, 57.33609, comma E99, degree of freedom 39, I get 0.02928, which is less than alpha. Which is less than alpha, so the informal conclusion let's reject null hypothesis because the alpha is 0.05. So step 6 conclusion. At 5% significance level, there is sufficient evidence to support the claim that the population standard deviation of the force transmitted from helmets to the workers exceeds 40 pounds. Okay. Now that's for this hypothesis testing on population variance or population standard deviation. Let me move on to 9.2. 9.2 is hypothesis testing on two populations. We will be comparing two population means. So what kind of case will that be? For example, just to give you some idea first, what we will be working on. For example, we try to compare the average height of, let's say, U.S. residents. Maybe we use U.S. male residents. U.S. male residents. Height. And Indonesian male residents height. And we want to say that in general, U.S. male residents, people who live in United States, tend to be taller compared to Indonesian males. Those males live in Indonesia. Now, I'm not saying that, notice that the hypothesis here is not saying that if you are US citizen or if you are descendant of somebody from US. No, I'm saying that those people who live in United States, regardless your race, regardless your heritage, you tend to have, you tend to be taller compared to those people who live in Indonesia, regardless what your race. United States is very diverse country though. So even though I do agree that we still have racism, but I also would like to say that it's not as bad as the one in other countries, at least compared to Indonesia. Now, also I would like to say that Indonesians' diversity is actually getting better right now. It's diverse. Indonesia is very diverse, but the racism is actually getting better compared to what happened around 30 years ago. Yeah, 30 years ago was bad. When I was doing my undergrad back in Indonesia, it's really bad. It's really bad at that time. They even say that there's a quota for Indonesian, even though I have Indonesian citizenship at that time, but because I am from of Chinese heritage, so they have unwritten law that how many Indonesian Chinese allowed to go to public school, like public university. Like in my department, I was the only Indonesian Chinese in my department. And in fact, I was double minority because I'm Indonesian Chinese and also a Christian. There were only 6 Indonesian Chinese in the School of Natural Sciences. Of like 6,000 students, only 6 of them Indonesian Chinese and Christian. That's how small it is. But right now it's a lot better. Okay. If Indonesia can get better in 30 years, of course, United States, which is more advanced, have a very good chance to get even better. Okay. And I have to say though, like 20 years ago when I came to the United States, the type of racism that I experienced and I witnessed was not as bad as the one I saw in Indonesia. And right now it's much better, especially because we live in LA, right? In LA, basically, this is the second melting pot of the world in America. You can find everybody here. And how do you know that you can find everybody? You can find any type of food you want. Okay, like not like in Indonesia or some other countries, like It's not easy to find. Like let's say if you are, let me talk about Indonesia because I know more about Indonesia, and I'm not talking shit about Indonesia here. Okay, I'm just trying to say that Indonesians' diversity, the racism in Indonesia and United States is still better. Why? Because in United States, any type of food you can find. You name a country in the world, you can find the food they serve there here. Of course, it may be more difficult, right? Okay. Indonesia, no, we have a lot, but not as many or as diverse as the one in United States. Like for example, I think in Indonesia, you have very hard time to find, for example, Armenian restaurant. It's very hard. It's very hard. Okay. Now in United States, you even have Armenian town in LA, right? Okay. Yeah. No, I'm not, in the example that I'm trying to bring up here, I'm not trying to compare people with United States heritage and Indonesian heritage. No, I'm talking about, I should not use heritage, like descendants maybe, huh? But I'm talking about people living in the United States tend to be taller compared to people who live in Indonesia, okay, regardless what kind of race you have. Okay, now then, let's say US male resident is the first group and Indonesian male residents is the second group. We want to show that the mean from the first group is higher, is taller than the mean from the second group. Okay, that's what we want to test. Okay, basically we are doing comparison of mu1 and mu2. Now, what about the modification? The modification will happen starting from step 2. So we still follow that 6 steps procedure, okay? But the hypothesis will be, am I recording this one? Yeah, I'm recording. Then the hypothesis will be, where's my pencil? The null hypothesis will be mu1 equals to, greater equals to, less than equals to mu2. Of course, the alternate hypothesis will be the complement of that. Okay. So there's not a lot of change. Of course, we know that we are comparing two population means, so it must be two population means come together. Now, but we have some issue with this way of writing, so we have to modify that further. In your test, you will write this first. You will write this first, and then you go on, modify that. Okay? I'm not saying that you don't write this. No. You still have to write this. You still have to write this. Okay? You still have to write that. Now, but then after you write that, you say then consequently, we are going to show that the null hypothesis, basically mu1 minus mu2 not equal to, greater equal to, less than equal to 0. Why do we need to modify that? Because we need to have a constant to use in our step 3. Remember? We need to have a constant to use in our step 3. Going back to our platform or framework we have earlier, right? The mu that we use here comes from this constant. Remember that? Okay. The constant that we have here will be used here. So we need a constant in the null hypothesis to use in test statistic, in our test statistic formula. Okay, that's why I modified that such that I have a constant. Now then, consequently, the alternate hypothesis will be mu1 minus mu2 not equal to, less than greater than 0. Which, if you think about it, I basically subtract both sides by mu2. I subtract both sides by mu2 such that I have 0 on the right-hand side. Okay, that's the step 2. Step 3. Test statistic. It depends on, do we know the population standard deviation for each one of them, okay, which is quite not common. If sigma 1, sigma 2 known, if population standard deviation for each group is known, then we will use z-score. That is x1 bar minus x2 bar minus mu1 minus mu2 over square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Basically, if you know the population standard deviations, then you will use z-score. That has been consistent to what we have done since very beginning, even in confidence interval case. Right? Now, however, if sigma 1, sigma 2 unknown, then we replace or substitute, by sample standard deviation from each sample. And of course, consequently, the formula becomes, the test statistic becomes T statistic. Minus mu1 minus mu2 over square root of sample variance 1 divided by sample size from the first sample, sample variance 2 over sample size of the second sample. Those are the modification. Now, for those who wants to know a bit more background about this formula, it has something to do with the foundation in the work, not central limit theorem, but on the way we prove central limit theorem in much higher level. We found out the following, that let's say x1 is normally distributed with mu1 as the mean and variance sigma 1 squared, and x2 as the mu2 and sigma 2 squared. Then when we add them, those two random variables, as long as both of them as long as both of them normally distributed, then the mean will be the sum of the means and the variance will be the sum of the variance. That's the foundation. Okay, so Thomas, what it has to do with that? It has to do with that in the following way. Imagine if you do the sampling distribution of this x1. So x1 bar with sample size n1. It will be normally distributed with mean mu1, right? With mean mu1, sorry. With mean mu1. Okay, the same mean, right? The central limit theorem, remember? The same mean, yet the variance will be the original variance divided by n1. Now, sampling distribution of the second group with size n2 will have the same mean, yet the variance will be original variance divided by sample size, sampling size. Now then, if I add these two sampling distributions, S1 bar with sample size n1 plus x2 bar with sample size n2, then it will be normally distributed with mean mu1 plus mu2 and variance sigma 1 squared over n1 plus sigma 2 squared over n2. See, if I try to write all of this in words, it will take me 1.5 pages. It's so long to explain. But once I write it in this notation, see this one notation here, actually summarize like at least 2 lines long sentence, you know. Okay. Now the thing is, this also applies when we subtract. Okay, when we subtract two sampling distributions, then the mean of that difference is the difference of the means. However, the variance of the difference is the sum of the sum of the variance. Okay, it's not minus here. No, it's not. Okay, it's still add them. The standard deviation, or I mean the variance, still being added. Okay. Now that's the background. At West LA College, around 13 years ago, we used a textbook that explained the linear behavior of normal distribution. The linear behavior of normal distribution, which is actually a nice property. That's a very nice property. Let me give you an example. This is off topic actually. You don't need to know this, but if you know, it will be great. Let's say we talk about gas. Okay. Let X be the amount of gas sold. And it is normally distributed with mean, let's say, from a gas station. Let's say the mean is 400 gallons with standard deviation 50. Let's say, okay. Now, and then we are told that the price per gallon is, let's say, $3. Okay. Now then, what is the earning? The earning will be 3 times the number of gas sold, right? Let's say the amount of gas sold from that gas station is 350 gallons. So what is the earning? It will be 350 gallons times $3 per gallon, right? Okay. Now then this 3x here, which is the earning, will be normally distributed with mean 3 times 400. And the variance is 3 times 50 squared. That's it, you know. Okay, so basically, if you know how the amount of gas sold and the fixed price per gallon for gas, then I can compute, for example, what is the probability that today's earning is more than $2,000, for example. Then that will be normal CDF, $2,000 to E99. The mean is 3 times 400, which is 1,200, right? And then the standard deviation will be 50 times square root of 3. Okay. So let's say, suppose you have a gas station and you already have, from history, you find that that's your number and the price on that day is $3, and somebody get into that gas station and then rob the cashiers. Then will the owner, and of course the gas station should be insured, right? So will the owner of that gas station claim that they lost $2,000 or more than $2,000? Hey, you know what, insurance company, somebody robbed my gas station and I need to file a claim of loss, right? And the loss is $2,000. Now then insurance company will come back to you and say, oh, you know what, let me see the history of your sales, okay, and the price of the gas per gallon for that day, okay, and then they do this computation and compute this. I think they will find out that no, you won't make $2,000 that day. Okay, I mean, I want to pay you your loss as an insurance company. It will be my pride to serve you, but I don't want you to lie to me either, right? Don't you think this is a really nice way to look into that, right? There's basically like this. What if the gas station actually purposely staged the robbery? Thomas, you have dirty mind. No, I'm just trying to say realistically, okay? Realistically, with this number, does it make sense for the owner of gas station claim $2,000 loss with that kind of history? No, it doesn't make sense. The probability for this to happen is actually very low. Not to say that, let's say the robbery actually happened at noon, which means you have not sold 400 on average. Let's say it happens at 12 o'clock at noon. Yeah, you have such crazy robbers. Then you don't expect the sales, you don't expect to use the sales at the end of the day that average 400. No, it doesn't make sense. Then, of course, the insurance company will reject it, right? Will they give you another offer? No, they will not give another offer because they feel that you are lying. Okay, so when it comes to insurance, don't lie since the beginning. Okay, don't lie since the beginning. Well, lying is not good anyway. Okay, I have a principle that if you really need to commit a crime, do it professionally. This is half joke, not really serious. I'm not encouraging you to do anything evil, but if you really need to do it professionally, that you don't get caught. Because once you get caught, nobody trusts you anymore. And that's statistic, right? How many samples of lie from a person, then you will call that person a liar, right? You just need a sample size of 1. In other words, it's actually really hard to be not a liar, right? With that category, then I will be a liar. Just like a lot of people say the same thing about Trump. Right now, it's not that I don't like him, though. No, it's just like the same standard will be used. If you use the same standard to any president, it will be the same. Every president's liars. Well, anyway, going back to this framework, step 2, you basically comparing two news. Okay, and step 3, the test statistic. If the population standard deviation is known, you use C-test. If unknown, then you use T-test. Most of the time, we use T-test. Something wrong with my writing there. I need to erase that, make it nicer to clarify that. So this is N2. Like that. Okay. Now, let's do an example. This one, my own example. This one, let's do my own example. Suppose, for example, that from a sample of 210 US male residents, we find out that X bar is, the average height is, let's say 70 inches with sample standard deviation 2.5 inches, while US Indonesian male residents, let's say 150 people, the sample size. The average height of this sample is 65 inches, which with sample standard deviation 2.8 inches. Okay, and then you want to test at significance level 5% that the average height of US residents, US male residents is more than the average height of Indonesian male residents. That's what we want to test. Okay, so I make up that claim. US male residents is taller, are taller, not is taller, are taller than Indonesian male residents. The number I use here are hypothetical, okay? That's not the number I use here are hypothetical. I just make up some numbers, okay? Even though I do believe that in reality, US male residents are taller, okay? But that's something I need to support with evidence. So I supposed to guess some sample and then compute it, right? But the number here are made up number, hypothetical, okay? Then, so I just show you the procedure basically. Then hypothesis. Hypothesis, the null hypothesis, alternate hypothesis, mu1 is greater than mu2. That's the claim, that's right there. The null hypothesis, therefore, will be the complement. Now, remember I told you that you need to modify that, okay, to get a constant on the other side. So the modification makes it becomes mu1 minus mu2 is less than equals to 0. So I subtract mu2 from both sides, greater than 0. Let me do my step 3 here. The statistic t, because we don't know the population standard deviation, it will be x1 minus x2 minus mu1 minus mu2. But what is mu1 minus mu2? 0. That's the zero use. The constant from the null hypothesis. I hope you remember that. Okay. Now then, on the denominator, we have square root of sample, the first sample variance. So I need to put a square there. That 2.5 is sample standard deviation. And to square it over the sample size 210 plus sample variance from the second group, the second sample variance over the second sample size. Then you compute that using calculator. Okay, don't forget, a lot of calculator parentheses play. Parentheses 70 minus 65, close parentheses, divided by the square root of 2.5 squared over 210 plus 2.8 squared over such a big number. I don't expect that though. Let me check. Did I copy anything wrong? No, nothing wrong there. So I'm okay. Wow, okay. And so that's 17.45772. 17.45772. Now then step 4, p-value. This is a t distribution. Test statistic 17 point something, and that's a right tail. So the p-value will be TCDF, lower bound 17.45772, upper bound E99, and the last one is the degree of freedom. Now the degree of freedom you use here will be the smaller of the first degree of freedom and the second degree of freedom. Okay, we will use the smaller of these 2 degree of freedom. So in this case, we'll use the smaller of 209 and 149. Now, can you follow me so far? Degree of freedom from the first group, the 210 is 209. Degree of freedom of 150 is 149. So I will use the smaller one here. The way to compute degree of freedom if you have 2 samples is actually very complicated. Just to type the numbers requires a lot of patience. It takes you 2 minutes just to type the numbers. So that's why we will not use that method. Okay, we will not use that method. We'll just choose the smaller degree of freedom. Okay, we choose the smaller degree of freedom. Okay, now then we use our calculator. Still here. Then it will be TCDF 17.45772. The upper bound E99, I just put a big number. Degree of freedom 149. Ooh, you see, I told you it's very, very small. That's 3 point something, 3.686 times 10 to the negative 38. Very small. That's approximately 0. Yeah, that's approximately 0. Okay. Now step 5, step 6, I think we can do it ourselves. Let me finish it up. So step 5, informal conclusion. Informal conclusion. There will be a reject null hypothesis. And therefore, step 6 conclusion. At alpha 5%, there is sufficient evidence to support the claim that US male residents are taller than Indonesian male residents. Okay. Now, calculator work. Calculator. We can check our work using calculator, but not really precise, because calculator actually get the degree of freedom using that complicated formula. Okay, now where do we get the calculator to confirm our computation? So our test statistic will be the same, but our p-value will not be the same with our calculator, because our calculator use different technique to get the degree of freedom. Okay, where do we get that? We go to stats, tests. You will go to two sample t-tests. Two sample t-tests. We use t, and it's from two sample, right? Okay, the data will be the stats for this x1 bar. X1 bar is, what did I use? 60 or 70. Sample standard deviation 2.5. And then sample size 210. And how about, I forgot the number. And then x bar 2 is 65, x2 bar, and then s2 will be 2.8, and 2 is 150. The test is right tail test. Pull, no, don't pull it. Okay, and then calculate. You see that we have the same test statistic, the same t. Our t are the same. Right? 45772. 45772. But our p-value are not the same though. Our p-value are not the same. Okay? We come up with the same conclusion. Now, so which is the correct one? Is it from the calculator or the one we use? The correct one is from calculator. The correct one from the calculator. Okay, that's the precise one. But notice that even though we don't use the same degree of freedom, this is the degree of freedom they have. That's the degree of freedom they have. But even though we don't use the same degree of freedom, therefore our p-value are different, but we still come up with the same conclusion. It turns out that in majority of the case, like nearly 100% of the cases, 99.999%, even though the degree of freedom are different that we use, as long as the degree of freedom we use here is the smaller of those two, then even though the p-value is different, the conclusion we get will still be the same. That is, either both reject null hypothesis or both fail to reject null hypothesis. Okay, so how do I know that you actually did not use, you don't do it by hand, you do it manually? I mean by calculator, you don't do it manually. If you give me a strange degree of freedom, the way we did our work, the degree of freedom has to be an integer. Okay, we use degree of freedom smaller, the minimum of the first degree of freedom, the second degree of freedom, which is the minimum of 209, 149. Okay, now the true degree of freedom will be a number more than 209, okay, but less than the sum. The degree of freedom that they have here, the degree of freedom that they have here will be more than 209, but less than the sum. Now it really depends on uh, how uh, the variance for each sample behave. Okay, so this is not really set in stone, such that people say, you know what, to be super safe, we use 149. For sure, the degree of freedom is greater than 149. Okay, now more things to say. Another reason why we choose a smaller degree of freedom is because in statistics we have a principle that we try to we try to underestimate the strength of our data. Okay, so let's say the sample size is 150, right? Okay, and then you have a multiple choice question and asking you what is the sample size. The sample size of 160, 140. Choose which one is the correct one. Well, you know that your sample size is actually 150, right? But you can only choose either 160 or 140. In statistics, you're supposed to choose the smaller one. In other words, even though we have a sample of 150, okay, and if we don't have that option, then we choose the option that has smaller sample size. Okay, that's how we underestimate the strength of our sample instead of overestimating it. That's the way we say that, you know what, this is just a sample, so there's a chance that it's not wrong. So instead of over present, instead of presenting the data as if it's stronger than it's supposed to be, we actually present the data as if it's weaker than it's supposed to be. Okay. Now, then going back, how to get the calculator, that's going to stat. And then you go to test. And then you go to tool, sample mean t-test. Now, why do we use t-test? Because we don't have the population standard deviation. Sigma 1, sigma 2, unknown. Okay. If they are known, then you use sample z test. Okay. Now with that said, let me ask you to do more problem. I did one problem earlier. Let me ask you to try this one. Let me ask you to try this one. The word significant more actually implies the alpha is 5%, but even if you don't know that fact, you will still use alpha equals to 5%. Okay, let me give you how many minutes to do this problem? Maybe 12 minutes. Yeah, maybe 12 minutes. So we come back at 10:03. Okay, try. When they say significant difference, so what is the sign in between?
I put not equal.
Yeah, that's right, not equal to. Because the claim does not imply which is taller, which is shorter. Or in this case, which is higher, which is lower body temperature. Okay, it's just say that they are different. Yeah, different means different, but doesn't imply greater than or less than. Okay, so later on you will see that, well, from step 1 we know this is the claim, but later on we will do two-tailed tests. Okay, now next I will do modification to have constant on the other side. And then step 3, test statistic. Equals to x1 98.105 minus x2 bar 98.394 minus mu1 minus mu2 is 0. I still have to write that 0 though. Okay, over square root of 699,742 square root of 0.699 0.699 squared over 65 plus 0.699 squared over also 65 as I remember. Then I use my calculator, parentheses 98.105 minus 98.394 minus 0 divided by the square root of 0.699 squared over 65 plus, oh sorry, my second number is not correct. Good thing I checked. My number here is incorrect. My number here is incorrect. My number here is incorrect. I need to change that. Yeah, earlier I used calculator. I didn't realize that it doesn't show up to you. 0.743. Sorry. Okay. My calculator went up here. Then I realized that's 0.743 squared over, happens to be the same sample size. That's negative 2.28403. Negative 2.28403. Do I copy that right? Now, if you want to cheat a little bit, instead of typing all of that in, you know later on you will do the test statistic. You check your work, right? And as I mentioned earlier here, our test statistic will be the same to what if we do it by hand. The p-value and the degree of freedom will be different. So at least instead of typing all those ugly number ins and not realizing we type anything wrong, okay, what you can do is you type that into your test. So this is actually a cheating. You still need to write this down though. You still need to write this down, okay? You need to write that down. But how you get this is not really by computing it, but by using calculator, okay? Instead of computing that, we will use calculator instead. So that will be stats. X1 bar is 98.105. Sample standard deviation 0.699. Sample size 65. The second one, the sample mean is 98.394. Sample standard deviation is 0.743. Sample size is 65. It's two-tailed test.
Professor, you put 98.384 on your calculator.
Should be 394. 394. This one here. Thank you. The difference is only 0.2. I'm sorry, 0.2 degree Fahrenheit. Yeah, but the p-value is already less than 5%. Do you realize? Do you see that? Yeah, that's the p-value, the actual p-value though. If we compute that by 10 later on, our p-value is very likely different. But at least I can steal the t, right? I can steal the t statistic and confirm that I don't get it wrong. Okay, now going back to our work, p-value, next to it, number 4, p-value it's two-tailed test. This is negative 2.28403. Whatever that is, I will need to double it later on. So p-value is 2 times TCDF, negative E99, negative 2.28403. Degree of freedom. Use the smaller one, 64 and 64. You have no choice, just 64. And then use my calculator to compute that. Okay, this is the actual p-value if we compute our degree of freedom properly. Okay, but if not, we just do a conservative estimate. If we use conservative estimate, TCDF, lower bound, negative E99, I make it super big number, upper bound, negative 2.28403, degree freedom 64, negative 0.012848. This is 2 times 0.012848, right? Multiplied by 2. That's 0.025 something. 2569670. So you see my p-value compared to what I had earlier. The p-value compared to what I had earlier is different, right? It's supposed to be 0.02402 using degree of freedom 1 to 7 something. But either way, I come up with the same conclusion that we will reject null hypothesis. Informal conclusion. Reject null hypothesis. In step 6, therefore, conclusion. At 5% significance level, there is sufficient evidence to support the claim that there is a significant difference between the mean body temperature of 4 men and women. Okay. Now, any questions so far? You see the crucial part is actually step 2 and step 3 especially, and then step 4, but I believe step 1 and 5 and 6 are just the same with what we learned before. Right? In fact, step 4 also the same to what we learned before. Okay. Now let me give you one more question to do. This time you do it from the beginning to the end. Earlier I actually give you a setup, right? So this time you do it from the beginning to the end. Number 11 in the handout. This should take you approximately, let's say it takes you like around 12 minutes plus 10 minutes break, 22 minutes. I give you 25 minutes. So together with your break, we come back at 10:40. 10:40, you are done with this. This is the short break with an exercise. Okay, let's call this your group 1 and this is your group 2. Okay, go ahead. I know you're still taking a break or still working on this, but let me just start early and then later on you can compare your work with mine. Okay, let me present this to you. Any questions so far? No question? No question? Okay, then if no question, I move on to the next section, 9.3. 9.3. This 9.3, the idea is actually quite simple, but the work is actually quite tedious. Okay, 9.3 is hypothesis testing on two population means. Dependent case. Or sometimes also called match pair case. Now, what's the difference between independent that you learned in 9.2 earlier with the dependent case? Now, in independent case, we deal with two different samples and try to infer to two different populations. It's a sample 1, and we have to infer something about population 1. Sample 2, to infer something about population 2. For example, when I talk about a US male resident and Indonesian male residents, there's no overlap. So we talk about people who are in United States and people who are in Indonesia, and not those people who are in both. Okay? Or the difference, the temperature difference, right? Male and female. So if you are male, you won't be counted as female. If you are counted as female, you won't be counted as male. Now, dependent case is as the following situation. You deal with the same objects. Let's say the same person, okay? The same person, a group of students, let's say, okay? Before and after treatment. Before and after treatment. So let's say about the weight of 10 people before a certain treatment and the weight of these people after treatment. And why we call that match pair? Because each individual, each item, each object of the first sample will give us a number. Let's say sample 1 consists of, let's say, 6 data. Okay, so data number one, let's say the weight is, let's talk about weight management. Okay, so let's say the first person have weight 150 pounds, second person 170 pounds, the third person 192 pounds. That's my weight right now. And then 210 pounds, and then 187 pounds, and 173 pounds. Okay, now then these 6 people get a treatment. After treatment, you can trace it. You can trace it. The first person from 150 becomes 130. 170 becomes, let's say, 160. 192 becomes 190. And 210 becomes 192. 187 becomes 185. and 173 becomes, let's say, 161. Now, when we say match paired, it means we can pair it before and after treatment. Before and after treatment. It's not the same to the case that we have before, in which the independent case, that people who get this number has nothing to do with this number. That's the independent case, right? Okay. In the case of dependent, when it is dependent, we can trace it with the weight of those who before and after treatment. You can actually associate that to the first person. The second person has weight before and after treatment. You see what I mean? So you can pair it. Okay. Now, so when we get a dependent case, it's usually being used if we want to compare the effectiveness of certain treatment. When I say treatment here, doesn't have to be what I said earlier, weight management. It can be like the effectiveness of an SAT prep, okay, or the effectiveness of, let's say, certain type of tutoring, or the effectiveness of, like in my case, I just remember this a long time, I don't mention it, but I remember I mentioned it before. In the past, when I was in 5th grade, I was the shortest in my class. Like among 45 students, I was the shortest guy. Actually, yeah, the shortest guy, but I was the second shortest in class. But then in 2 years, after I played badminton, in 2 years, I was actually the second tallest in class. So in that 2 years, my growth rate is a lot faster compared to my classmates, such that when we get to the 7th grade, I was the second tallest. Now, can you imagine what that badminton doing? You know, so can I then claim that badminton make me grow taller faster? Now, of course, you cannot just do sample of one person, Thomas, right? Then, but at least I start with that kind of hypothesis, right? So if I want to say, tell other people, oh, you want to get taller, go play badminton. Before I do that, I need to ask people around my age at that time, 5th grade, and then maybe get 5 people, like 10 people, 20 people, and then measure their height in, let's say, 1 year or 2 years, and measure them again in 2 years. Now, then from there you can see, oh, you know what? Yeah, if you play badminton, you will get taller, right? Okay. Of course, people without playing badminton when they were 5th grade, if you measure their height 2 years later, they will be taller. Okay, but the height gain is actually more compared to those who don't play badminton. Okay, now that's another story. Basically, you want to see, in this case, what is the effect before and after treatment. Okay. How will that be done? The modification. The modification actually not done in the steps, but it is done with the data. So what will happen is you have data 1. Let's say this is the data before treatment and this is the data after treatment. Okay. Now we will define D. We will define D as the difference of data before and data after. So you will have a bunch of D's here, right? You'll have a bunch of D's. Now what you will do next is find how many data you have. The number of data is basically the number of differences you get. Let's say you have 1, 2, 3 here, so your N will be only 3. Even though you actually have 6 data, but you get 3 differences. Okay, you will get 3 differences. Now, from those D's, you will find the sum of D's and the sum of D squared. Now, the purpose is, once you get that, you will get the D bar and the standard deviation of the differences. So this is our first stage to find the D's, the number of data, the number of pairs, right? And then the sum of these, the sum of D squared. And then we find the D bar and standard deviation of D. Let's do it this way. Let's do it this way. Let me just borrow this data again and ask you to do those computations. Let me ask you to do this computation. I want you to find the differences. So let's call this before and after treatment. After, call this the D's, the difference. Okay. Now you may want to do it this way. You may want to do it this way. After you get the D's, get the D squared. So later on your N will be 6, right? Your N will be 6. There are 6 pairs of data. Okay. Now then after you get that N, well, you have that N, that's 6. Find the sum of D, which is something you get from here. And find the sum of D squared, which you get from here. Now then, after that, find the D bar, which is basically the sum of these divided by the sample size. And then find the variance of those differences, which is the sum of, I believe you recognize these formulas. I just replace X by D's. And then you find the standard deviation of these differences. How long do you think it takes you to do this? Let me give you 10 minutes. So we come back after 10 minutes. So 11 o'clock. Okay, you do this first. After this, it will be easy. After this, it will be easy. Okay, that's 1110. Can you check if I got it right? If not, let me know which mistake I made.
I got the same thing.
Got the same thing? Okay, good. Now, so that's the procedure to get the sample differences, the difference of the samples. No, I think I should say the mean of the difference, sample mean of the difference, and the sample variance and sample standard deviations of the differences. Now, then what happened to the modification? The modification actually starts in step 2, hypothesis. In the independent case, you will see we basically continue from what we did in independent case. So we have mu1 equals to greater equals to less than equals to mu2, which we modified to be mu1 minus mu2. Okay, now in our situation here, we actually modified even further. We modified even further, making it mu d. Mu d equals to greater equals to less than equals to 0. Mu d is not equal to less than greater than 0. Of course, feel free to just go ahead from here to here. You don't need to write the second step. Just go ahead from here. You have to write that one, and then you can go to here. Okay. Now, some students, they say they prefer to write this middle step first, and if that's what you feel necessary, go ahead, go for it. Okay. But if I allow you to skip steps from, you have to write this, you have to write this. Okay. Now then, step 3, the modification on step 3. On the test statistic, it will be a t-test. Because we don't have the samples, then we don't have the population standard deviation. We have the sample standard deviation of the differences. So you will see the formula I use here is actually the formula from the t-test that we have for one population mean. One mu. It's very, very similar, but I just change the x becomes d. So the formula will be d bar minus mu d over sd over square root of n. Now compare that with the test statistic for one population mean with unknown population standard deviation. T equals to x bar minus mu over s over square root of n. Do you see the similarity? You basically change the notation. Instead of x, you make it d. Instead of mu, you make it mu d. Instead of s, you make it sd. For the differences. And of course, then in step 4, that will be TCDF. Okay, that will be TCDF. Now, that's the modification to the work. And you see the hard work is actually happen here. Okay, suppose I continue from there, the claim, the weight loss program is effective. Now, if the weight loss program is effective, then the average before and the average weight before the treatment should be more than the average weight after the treatment. Right? Supposed to be like this. Okay. Remember I say it's weight loss. So you're supposed to lose weight. Okay. If I say weight management, that's different. Okay. Weight management is different. By the way, weight loss means you want to lose weight. I know that's actually the majority of the case, especially in America. Okay. But weight management program is actually more general than just weight loss, especially in Indonesia, for example, and not only Indonesia, in a lot of countries, especially in Asia or Africa, where hunger is still quite common. Weight management program will actually put you to appropriate weight according to your age and your height. Like, for example, in Indonesia, in some region, a lot of them actually underweight. Okay, so weight management program will help them gain some weight, of course, including muscle. If your weight is less than supposedly, then very likely it's because your muscle is not well developed yet. Okay, and muscle is more dense compared to fat. Okay, so it is possible you go to gym, and this is actually quite common. You go to gym, the first one month, you actually gain weight. Why? Because you trade your fat. You trade your fat to muscle. Okay, that's why you will experience some weight gain at the beginning of your gym, and then if you continue, you may start losing, but that's basically because you start losing more fat compared to the gain of your muscle. Okay, now that's what I heard from those trainers though. I actually live next to pretty much very close to 24-hour fitness. So before the pandemic, my wife actually going there. I myself actually went to LA Fitness before. Okay, mu1 less than equals to mu2. But the claim is the weight loss program is effective. So this is the claim. And then this is a right tail. Okay, now I modified that right away to the mu-d style. And null hypothesis will be mu-d less than equals to 0, mu-d greater than 0. Now step 3, test statistic. Will be t equals to d bar, which is 10.66 minus mu-d, which is 0, over the standard deviation 7.65942. 7.65942 over square root of 6. Of course, somebody will criticize you for using only sample of size 6. Okay, but if this is your preliminary survey, preliminary research, preliminary hypothesis test, with 6 people, you have a very strong data, then you increase your sample size. Okay, you don't want to start with a sample size of 300 just to find out that there's no difference. Okay, you don't need 300 actually. You start with a small one, okay, and then you slowly increase that. Okay, in reality, that's the case though. You don't start with like 1,000 right away. Okay, yeah. Of course, you don't release your data if you have sample size of 6. Okay, so people will be laughing at you. Okay, you will increase this later, but for us at the beginning, especially this is just an example, right? Yeah, we start with 6. Okay, so this will be, let's see, 10.66667 divided by 7.65942 in parentheses square root of 6. Earlier I forgot. Okay, I get 3.41121. Then my step 4 p-value, it's a right tail. This is 3.41121. So the p-value is TCDF 3.41121 E995. That will be very small. So even with 6 data, we already have sufficient evidence to claim this thing. But if you present this to somebody else, they will question, you only have 6 data here. Even though we know our 6 data, even though it's only 6, but the result is very strong. The result is very strong. This is even stronger, this is strong enough to reject null hypothesis, even if the alpha is 1%. Okay, even if the alpha is 1%. This is less than 1%, by the way. Okay, barely, very close to 1%, barely less than, but that's a good start. So step 5, informal conclusion. That will be reject null hypothesis. And then step 6, conclusion. At 5% significance level, there is sufficient evidence to support the claim that the weight loss program is effective. Okay, so this is the detail, but as you can see, a lot of work actually is done here. Okay, any questions so far? So the hypothesis testing, the hypothesis testing part is really just doing the t-test on one population mean. And the sample we have, instead of X, the sample are these, the differences. Now we apply hypothesis tests on those differences and show that the difference on average is greater or less than or not equal to 0. Okay, so in other words, I basically have taught you how to do this. We just apply that to the D's. Now, what I'm about to teach you now is how to use calculator to compute this a lot faster. And I have that plan later on in my test next week. When I ask you this kind of question, I will ask you to give me the D's. I will ask you to give me the D's. I will ask you to give me this. Okay, I will ask you those questions, but at the same time, I want you to also teach you how to use calculator to get these numbers without actually computing them. Okay, call that the cheating way. Okay, call that the cheating way. My purpose is that after this class, if possible, you can tutor. Okay, if possible, you can tutor. And there are two people actually in this class doing very well, just like in my summer class, the test that you took actually from my summer class. And I have like 2 or 3 people there also doing extremely well. That's why I use this test again. Because it works in 8 weeks, right? It works in 8 weeks at West LA College. So I assume it's supposed to work well here, right? Okay. I have an honest expectation that, well, if I have some people getting more than 90s there, actually 2 people getting more than 90s there, then in this class I should get more or less the same number of students getting more than 90s. And it turns out that I have 3 people get more than 90s and 2 of them get more than 100. The highest score is 104. The second highest is 101.5. Somebody get 93 as I remember. Well, anyway, that's why I use that test, because in the past it gives me good result without compromising the difficulty of the questions, you know. Then I use that test again in test 3. Now, in your test 4 later on, you will have quite heavy, tedious computation. And I would like to teach you how to use your calculator to still give me the number I want. Okay, give me the result I want, but in a lot faster way. So I try to benefit from your TI-84. Okay, now let's see what data I have here. I have list 1, 2, 3. Okay, let me clean up the data first. Okay, so I go to stat, clear list, list 1, clear list 1, clear list 2, and clear list 3. Are you with me? So doing this command to your calculator will clean up your list. Okay, will clean up your list. Now, what I will do is the following. I will enter all this data, list 1 from my first column, and make sure you key those numbers in that order. 150, 170, 192, 210, 187, 173. Are you okay with this so far?
Yep.
Okay, then I go on with list 2. Make sure what you have in the first row correspond to what you have in the second row. Okay, so the second column, first row is 130. That's the one associated to the 150 in the first column, right? Okay, and then 160. Remember, this is a match pair. So the one on the left-hand side should match with the one on the right-hand side on the second column. Okay. So I have list 1, list 2. Now, I will teach you now how to get these D's super fast. What you will do is you move your cursor to the third column. Do you see it there? Okay, now move it up to that L3. Let me screenshot that so that I can point out to you. So in your calculator, so you occupy the column 1 and column 2, and your third column, your cursor has to be here. Your cursor has to be there. And we will insert the command L1 minus L2. Okay, I will insert the command L1 minus L2. So basically, I will use column 1 minus column 2 row by row subtraction. And it is by list 1. Do you see that? Do you see that here? Okay. Minus list 2. Are you with me? Should I screenshot that? Let me do so. So this one here, while this is there. Okay. Now then I will press enter. It will fill it up for me. Press enter. Then it will give this. Okay, it will give you the differences. Okay, so we got all of these already. Okay, now how do I get, now we will get the n, the sum of d squared. How do we do that? Go back to your calculator. Okay, you will perform one variable stats on L3. So you go to stats, calculate one var stats on L3. On the third set of data, frequency list, don't worry about it, calculate, boom. But when you use L3, our calculator understands that as X. That's why they use X bar, sum of X squared. But you actually use a dummy variable D, right? Okay, so your N will be 6. Your sum of D will be 64. And sum of D squared will be 976. You see that? Maybe I write it in this way. And sum of D squared. Sorry. This guy go here. This guy go here. And this guy go here. Okay, therefore, using those, D bar will be, then you pretend you write that sum of these, which is 64 divided by 6. Just pretend that you compute it, but then you look at your calculator, oh, that's 10.66667. You see what I mean? Okay, and then how about the variance of the differences? the variance of the differences, then you say, oh, 6 times 976 minus 64 squared over 6 times 5 equals something I don't know, but the SD will be 7.65942. Okay, now then you use your calculator just to confirm that you don't make any miscomputation. Parenthesis 6 times 976 minus 64 squared, close parenthesis, divided by 6 times 5, which is 30. 58.66667. Now do the square root of that number. Do you confirm that? So I use that one for stats. I use my calculator to confirm what I get, right? And you get the sum of these squares super fast. Instead of doing it by hand, you basically use your calculator to compute that for you, right? You get the d's by using calculator computing it for you. And then you go to, you go to stats, calculate one for stats of that, the third list, give you this. Okay, now in fact, if you want to do the hypothesis test, remember you do hypothesis test on the t-test, right? So you go to stat, test, t-test. Now perform that t-test on list number 3. Okay, so I can do it this way. Go to data, and they will ask you what is the mu naught. The mu naught is 0. Okay, let me put that there. Okay, continue. So I do it below here. So you do t-test, one variable t-test. I use data, because remember your data already stored in the third column, right? Okay, and you do against mu naught, the constant of null hypothesis is 0. That's the constant H null. Okay, and this is the notation you have in alternate hypothesis. Okay, I'll go back to my calculator. I will compute that, and it gives me this result. Now you can confirm my test statistic here, 3.41121. 3.41121, right? Okay, and then my p-value 0.00951. My p-value 0.00951. Okay, compare this to what we did manually. In other words, if you really know how to use your calculator, you still can give me this step 1, 2, 3, 4, 5, 6 with very, very less computation. You still need to write this thing. You still need to write this thing. You still need to write this, right? Okay, but don't you think it's really nice that you already know the outcome? You just need to show the work. It's really nice if when you date, you already know you will marry this person, but you still need to date, right? That will be a joyful time of dating, right? I think when you date somebody that you don't have confidence that you will end up marrying, that will be struggle. Actually, that will be a daily struggle, right? Because it's like, I don't really know. Imagine if I have that. I don't really know if I'm going to marry this person, right? The sample data I have seems like it's inconclusive. It's insufficient evidence to support the claim that she is the person I'm supposed to marry. Okay? Then in that case, what should I do? Should I increase my sample size by dating this person more? Or should I just like, you know what, forget it, let me move on? That's not the joyful time. But imagine if you already know the answer. Oh, you know what, my test statistic will be this, my p-value will be this, my conclusion will be this. Okay? And there's sufficient evidence to support the claim that this is the person I'm supposed to marry. Don't you think this is really nice? Imagine if you know that on day one of you dating. That will be so nice, huh? Okay, so imagine that what I'm offering you is that suppose you know the outcome, you just need to do the procedure. Okay, you just need to do the procedure. So I will give you one problem right now. I'm about to give you one problem right now. I want you to still show me these 6 steps. I need you to show me these 6 steps. Of course, on the top of that, I need you to show me this. Okay, but use your calculator in educated way, such that even though it seems like you show your computation, you actually have your calculator helping you a lot. Make your TI-84 that you spend so much money on worth it. Okay, and of course I don't write this down, but it is recorded. I hope one day you can make money from what I teach you here. East LA College, just like a lot of other colleges, requires most students to take statistics. So the market is out there. If you can tutor them, that's a lot of money there. Okay. Remember the ELAC book sale? How many of you remember that group on Facebook? ELAC book sale or ELAC students. There are actually 2 big groups at East LA College. Be a member there. And at the beginning of the semester, or let's say in the winter, the request for winter will be very high. There will be a lot of people asking for help in tutoring stats. And you can market yourself there and charge them $25 per hour. If you know how to use Zoom, okay, Zoom I think is only $15 per month. In that $15, in that 1 month, you can tutor so many people already and you get so much money. $20 per hour, you tutor 5 hours per week, that's already $100. And you just do it from home. Don't you think? A lot of you have that dream, right? Work from home, right? Now your dream may come true. Will you do that? Hey, I'm serious right now. Anybody say amen? You want to work from home, now you get it. Will you do that? You have the skill, you have your computer, okay? You have that $15 to make $500 per month, okay? And you don't need to drive. And believe it or not, that's tax-free. I don't think, I mean, come on, nobody will report the tax for this. I mean, if you want to go ahead, I will not recommend that though. Okay, hassle, more paperwork, right? As long as that person shut up, don't give your social security number to that student, then you should be fine, right? Thomas, you teach me how to be evil. Yeah, I teach you how to get away from IRS. If nobody tell them, they won't know. The reason you go to work and need to pay your tax is because your employer have your social security number and report it to IRS that you get how much paid. That's why at the end of the year, if you don't report that, IRS will come to you. right? Okay, but when you do personal tutoring like this, trust me, it will be really nice, you know. And if you can get 2 students only 2 students, that's already $1,000 per month. Okay, at least. Okay. I believe I mentioned that I have 1 student at UCLA. West LA College is actually not too far from from UCLA. So he tutored at West LA College while doing his bachelor at UCLA. Now, it turns out that after tutoring for 1 or 2 years, he figured out that the demand for his tutoring is a lot more compared to other tutors. So he decided, you know what, I will cut my hours from 20 hours per week. I will cut it down to 10 hours. Okay. And then I will take more students on the outside. And of course, he asked permission from the tutoring service because he doesn't want to have like, hey, how can you tutor these students and still get paid from that students, you know? So as long as he tutors from the library at West LA College, he won't get paid from the students. But if he does it outside of his tutoring time, outside of his service to West LA College tutoring center, then he can get paid from student directly. Okay. And after doing that enough, he later on said, you know what, I won't tutor at West LA College anymore. In fact, he actually gets Zoom. Even before the pandemic, he already started using Zoom. And he charged $50 per hour. Yeah, of course, this $50, I think is for 2 students. For 2 students. 1 student will still be $50, and for 2 students, I think either $50 or $60 per hour. And the nice thing about having Zoom, he doesn't need to drive anymore to West LA College. He just do it from his door. Okay, and no traffic. You know, West LA College and UCLA area, a lot of traffic. He saved time. He basically log in, log out, and then suddenly have another student, He paid for his tuition this way. Okay, so don't underestimate this though. Oh, when I say tuition, I also include, he told me that this include basically his rent, his tuition, his food. So I want to teach you something you can make money on. Okay, a skill that you can market. And I hope some of you can benefit from this. Okay, 3 of you can benefit from this. And it doesn't have to be my student. Okay, of course, if you want to tutor my students in the winter, let me know. Okay, let me know, and I will announce your name and phone number or email in my winter class. Okay, if you want to. Okay, but it doesn't have to be my student. Other students will be fine. The skill I teach you here is more than what the skill that you need to know to tutor anybody. Okay, now let me give you 1 problem at which you should be able to apply what I teach you. But you need to see that from my handout, hypothesis testing procedure 3. Let me find the question that is appropriate. Let me use this one, not too hard one. I think this is the last question or second from the last question from the handout 3 I gave you. So this person, William Gossett, he is the person who invent t-distribution. He would like to know, so he apply what he get into the following situation. There are 2 types of seed, the regular seed and kiln dried seed. Okay, and he plant this on different plots. Okay, But each plot, so let's say in region number 1, maybe I draw it this way. Let's say, oh, sorry. Let's say in region number 1, he has 2 plots. That's the regular one, and this is the kiln dried one. There's another plot. He will plant both next to each other. Another one, somewhere else, regular kiln, somewhere else, regular kiln, and somewhere else. Okay. I think there are how many? 11 such plots. Okay. Now, what he tried to test is he tried to test that the type of seed affects the yield. In other words, the average yield from the regular seed is not the same to the average yield to the kiln dried one. Okay, but of course he needs to get the difference, right? Okay, so of those 11 plots, he get this result. Okay, now what do I want to get from you? I need you to get the D's, sum of the D's, sum of D squared. I think the n is easy, the n is 11. Okay, now after that, get the D bar, and then variance of the differences and standard deviation of the differences. Then you perform hypothesis testing. Okay, the claim is the type of seed affects the yield. That will be the claim. And the alternate hypothesis will be like this, which later on becomes, when you modify to get a constant on the other side, that will be mu d not equals to 0, which means it's a two-tailed test. Okay. Now, let me ask you to do this. Right now it's 11:52. I want to give you a break at the same time. How long do you think you need to do this? Let's say, will that be too much if I say that you will need around 6 minutes for this? 6 minutes for this, and then 10 minutes for those 6 steps, plus 30 minutes break, the long break. So we come back at 12:40. Will that be reasonable? I don't want to give you too long a break too, but I want to make sure that you really know what you do also. Will that be okay? Or 12:30, which is good. 12:40 or 12:30. After this section, I have 9.1, and that's it. So after 12:40, one more section, and then we're done. Okay, that it is then. So try to do this, finish from the beginning to the end. Okay, all this information here. Let me scroll it down a little bit so that you know what I want. Okay, and then don't forget the step 1, 2, 3, 4, 5, 6. Okay, we come back at 12:40. This is what I get from my calculator. Please check. I think that should be the same to what I get 2 days ago. Yeah, 2 days ago, I taught the same thing at my West LA College class. Is this okay? But yeah, I get this from my calculator though. Okay, I get this from my calculator. And then I will do the hypothesis testing then. Let's start the claim. type of seed, affects the yield. And then second, hypothesis and null hypothesis, alternate hypothesis, mu1 equals to mu2, mu1 not equals to mu2. Am I recording this? Yeah. And let me modify it first. So null hypothesis, this is mu d equals to 0, mu d not equals to 0. The claim is here, and that's two-tailed. Then step 3, test statistic. T equals to, the difference is, I think it's negative 33 here. It's negative 33.72727 minus 0 over SD is 66.17113 over 11. You know what? Let me cheat. I somehow start thinking, is it what I get 2 days ago? So 2 days ago was what? 2 days before, so should be December 2nd, huh? I get a different number. No, I get the same number. But I make mistake on the denominator. What's that? This one. Yeah, I make mistake here. I forgot to put the square root. Yeah, I should put the square root. My bad. Oops. What am I doing? I should put square root. Now, okay. Because when I compute this visually earlier, that's around 5 point something, negative 5 point something, not supposed to. 33.72727 divided by 66.17113 times square root of 11, that is negative 1.69048. So step 4, the p-value Yeah, I try to squeeze the space here so that you can have a better window view window. But in your test later on next week, you don't need to try to save space. Okay, I will give you 1 page per question. And because it's two-tailed, I multiply by 2. So p-value, that's 2 times TCDF, negative E99, negative 1.69048, degree of freedom 10. 0.060908 when I multiply by 2, that's 0.12182. Now, of course, you can use your calculator to find this p-value, right? Okay, and then step 5 is more than 5%. So informal conclusion. That's failed to reject null hypothesis. And therefore, step 6, conclusion. At 5% significance level, there is insufficient evidence to support the claim that there's insufficient evidence to support the claim that the type of seed affects the yield. Okay. I would like to do more things from here. Two more things. What you should not say, don't say it incorrectly. Unfortunately, our journalists, newspapers usually quote the summary said by an official incorrectly. And what makes it worse, we as the listener, we as the reader of those newspapers do not try to check what the newspapers say, and we have some misunderstanding. Okay, one thing that I read is this, that Department of Justice, Department of Justice says that William Barr say that, this is from the news, says that there is no evidence of election fraud. That's from the headline of the news, right? But there's a problem with this statement, and there's a problem with this statement, first of all, okay? Because when we do statistic, when we do hypothesis testing, we never say there's no evidence of fraud. Not supposed to, okay? Simply because you don't see it doesn't mean it's not there, okay? Trust me, the same apply to everybody's brain. Simply because I don't see your brain doesn't mean you don't have brain, okay? Simply because you don't see my brain doesn't mean I don't have a brain. In fact, even after you see my brain, you don't have any evidence that that brain is working. You don't have any evidence that my brain is working, okay? But no, we never say it that way, okay? We never say it that way. It's always that there's insufficient evidence, there's not enough evidence of fraud. Now, the thing is, when you actually look at what this William Barr actually said, he actually said a longer sentence. There is not enough evidence of fraud that will flip the result of the election. He didn't say there's no evidence. He said that even if you can find any evidence of fraud, it is insufficient to flip the result of the election. That's what he said. Okay, but because those medias, and it's not only one newspaper, it's actually New York Times, Washington Post, they try to say it, they may argue that they try to say it in a shorter way in their headline, right? But that's a technical statement though. It's different to say there's no evidence of fraud, okay? Which means if I can show you one evidence of fraud, then what you say is wrong, right? But no, what William Barr said was not there's no evidence of fraud. What he said was there's not enough, not sufficient evidence of fraud that will flip the result of the election. That's what he said. Okay, now, does it mean that he already come up to a conclusion that if you have any extra evidence, you don't need to submit that anymore? Well, they need that. That's why they said there's not enough there's not sufficient evidence. If you have more evidence, give it to me. Okay, but you should not scream that we have evidence without showing what evidence is that. Okay, so there's a big difference between saying not enough evidence and there's no evidence. Those are two different things. Okay, my wife have enough evidence to say that I'm a jerk. Okay, I think I say it wrong. My wife have evidence to say I'm a jerk. It's just not enough to say that far. Okay, I mean, come on, man. I'm a human being. I say wrong things at times. I get mad at times. I say things that I was so sorry and I apologize for that, right? Okay, but is it enough then to say, Thomas, you move on with your life, I go on with my own life? But apparently not. Those are two things though. So what the media try to say and what they say are two different things. Be very careful with what you read right now. Okay, they may say that they just try to say it in a short way, but when they shorten what they try, when they summarize it, they end up with different summary. And apparently, this journalist didn't study statistic enough. Okay, now then they will say, like, if you leak this, what I say to mass media, they may say that I claim they don't study statistics. And they show me their transcript. No, that's not what I say. What I say is they didn't study enough statistics. Okay, because if they did study enough statistics, they will not cut the wording like this and treat that as if they are the same. No, they are not. They are not the same. Insufficient evidence doesn't mean there's no evidence. It's just insufficient. Okay? That's one. Second, I think this is more important. What I teach you here, just like especially the two parameters case, the one before, may very likely be used even when you transfer. So what I have in mind is to teach you what you can use when you do research in future. Now let me share with you my Excel. Wait a sec. I do this one. Okay, I will show you how to use Excel. Okay, and in fact, let me use new data. Let me use this data here. This is the data from Boston University School of Public Health. Can you see what I have here? Yeah, right, School of Public Health. And they try to see if a new drug can really lower total cholesterol. Now then they get 15 people. They measure the cholesterol level before and after the treatment. So I will copy this data. Okay, I copy this data and I put it on my Excel. Why it looks like that? That's not what I want. that's not the right one. Okay, go back. I want to get this data here, from here, all the way to here. Oh, you know what? No, still not good. How about this? Ah, now I understand. It treats it as a... I wonder how to do this better. Right there. Ah, now I know. Okay, give me a second. Let me get the original data from Word. I took it from PDF file earlier, and PDF file will treat that as words instead of table. Now, I think if I take it from here, it will give me a better result. But you need to be patient with me. Yeah, it will treat that as a table right now. Okay. Can you see that on my Excel? Now then, I will just call this difference D. Okay, and then the next one, the next column, I will call that D squared. Okay. Now then my D will be equal to this guy minus this guy. So I'm trying to teach you how to use your Excel, because when, for example, you do a research of for just 15 pairs like this, I don't think you will ask your professor, you know what, I need TI-84 and I need to get that $100 funding to buy a calculator, and I need to go to Staples to buy it, you know, and trust me, your professor will say, you know what, F this shit, you know, I find somebody else. Why? I have computer. You don't know how to use computer. You ask for TI-84. The computer is there. Use that computer. Okay. So nah, you use computer. That's what I get. Okay. That's what we get. And this guy here will be the sum. This guy here, I need to do this guy here also the sum. This guy. Why does this is the sum? Okay, now it works. Okay. Now then, so that's the D squared, the sum of D squared. My N is 15. My sum of these is 254. Sum of D squared is 710. Let's make the numbers. I don't like it. Okay, now then, how about D bar? D bar is equal to this guy over this guy. Okay? This guy, the sum of D divided by sample size. You can increase the number of decimal places if you want. Now I have 5 decimal places, right? And then how about my S squared D? the variance of the differences, that's equal to 15 times the sum of d squared. What am I doing? I need to use equal sign here. Equals to parentheses 15 times the sum of d squared minus the sum of d being squared divided by parentheses the sample size times parentheses sample size minus 1. Therefore, the standard deviation of the differences will be that guy to the power of 1/2, 0.5. That's my D, standard deviation. Now, then how about your test statistic? T stat will be parentheses on the numerator, that will be the D bar minus 0, close parentheses, divided by parentheses standard deviation of the differences divided by the square root of 15. So square root is to the power of 0.5. That's the T stats. Okay, now how about the P value? Now you want to make sure that the cholesterol is actually lower, right? Cholesterol is lower, so the baseline should be higher than 6 weeks later. Means it will be a right tail test. Okay, then it will be TCDF, right? But the way it is being done in Excel, they have different formula. It's T distribution right. I happen to have it there. Oh, let me show it to you. This is T distribution right. This is right tail. This is 2T here, that's 2 tail. And this is T distribution, that's a left tail. Okay, I want the right tail. Okay, now from the test statistic, let me plug it here. Now, because it is right tail, then it will be from that test statistic area to the right. Now, the degree of freedom will be this guy minus 1. That's the P value. So you see, since the beginning to the end, I don't use TI-84 at all. Okay, from the beginning to the end, I don't use TI-84 at all. Now, my purpose to show you this is, let me make it a bit smaller. My purpose to show you this, to show you that it's actually doable using TI-84. Okay, so you tell me later on, oh, you know what, I don't know how to use TI-84. I don't know how to use Excel, but I know TI-84. I was just like, okay, you learn how to use calculator, but you don't learn how to do stats. I still need you to know how to use stats. Okay, now that's for this 9.3. Let's go back to our main work. The last part, 9.4. The last part here is actually on the easy side, a slight computation. Seems to be tedious, but it's not. Hypothesis testing on pool population proportion. I'm sorry, that's not 9.4. It's 9.1. It's 9.1. My bad. 9.1. So we are comparing the proportion of people doing something and proportion of people not doing something. Now, basically, the data given to you will be mainly the sample size from both samples, and then the number of successes or number of people falling into certain categories of those n. Now from there you will get P1 hat, which is basically x1 over n1, and P2 hat is x2 over n2. But there's one, so to find the P hat is easy. That's something we did before. But we have something new called P bar. It means pole proportion. That's when you get this data all together, you pull them, you combine them. It will be the number of success altogether over the number of trials or the sample size altogether. Okay, imagine if you put them together in the same class. Okay, so imagine if the first group is the proportion of students passing Thomas class, and the second group is the proportion of students passing Stephen's class. Mr. I wonder if you know Mr. Huang. He's the instructional assistant, basically the supervisor, almost you can say the supervisor for the math lab at ELAC College, together with Mr. Eddie Hidalgo. So let's say you want to see the proportion of students passing Thomas stats class and Mr. Huang's stats class. Okay, so you get the number of people in Thomas class and how many pass, the number of people in Mr. Huang's class and how many pass. Then from each those, you get the proportion of students in Thomas class who pass and the proportion of students in Mr. Huang's class who pass. Now, this will be the proportion of students in those two classes who pass. Okay, now going back, let me erase all the yellows. Now, the modification will be done in step 2, and actually only step 2 and step 3. In step 2, hypothesis, we are comparing two proportions right now. So the null hypothesis, alternate hypothesis will be about P1 and P2 equal to, less than equal to, greater equals to, not equal to, greater than, less than. Notice that it's actually just the same to comparing to population means, but this time instead of population means, we use population proportions. So we change the mu into p's. Okay, step 3, test statistic. Test statistic. Just like before, when it comes to proportion, we use C. Right now, we use C also. But then the formula will be P1 hat minus P2 hat minus P1, P2. It mimics what we have in pool population means case. Z equals to x1 bar minus x2 bar minus mu1 minus mu2 over square root of something over n1 plus something over n2. Okay, so those were the best point estimate for mu. This is the best point estimate for proportion. Okay, this is the number from the null hypothesis, the constant from the null hypothesis. This will also be the constant from the null hypothesis. Okay. Oh, by the way, I need to modify this to get the constant. Null hypothesis equals to P1 minus P2 less than equals to greater equal to 0. alternate hypothesis P1 minus P2 not equal to greater than less than 0. Now then, the painful one is on the denominator. That will still be something over n1 plus something over n2, like what we saw here. Okay, very, very similar. But the difference is on the numerator, it is actually P bar Q bar. P bar Q bar. That's the test statistic. And because it is C in the test 4, it will be normal CDF. Okay, now let's see. Hypothetically, I make up numbers for my first example. Example 1, I may give you only 2 examples due to time. So example 1, let's say a test at alpha equals to 3%, the claim that Mr. Huang's, by the way, Mr. Huang is my best friend, one of my best friends. So even if the result says that he is better or worse later on, doesn't matter, he's still my best friend. Okay? And the numbers here, of course, hypothetical. Claim that Mr. Huang's passing rate is higher than Thomas' passing rate. Step 1, claim Mr. Huang's passing rate is higher than Thomas. And let's say here's the data from Thomas' class. We can call that the first group. Okay, the number of students in that class, let's say 12, and the number of students passing is 4, while in Mr. Huang's class, there are actually 17 students, and then the number of students passing is, let's say, 8. Okay, now let's get those 3 important proportions first. P1 hat, find that out. P2 hat, find that out. And then P bar. Once you get P bar, also get Q bar. P1 hat is 4 over 12. That's 0.3333. I need some space. I don't like it there. That's 0.33333. And P2 hat is 8 over 17. That's 0.47059. Now P bar is the total number of people passing, which is 12, over total number of people taking those classes, which is 29. That is 0.41379. Then the Q hat is 1 minus that is 0.58621. That's the setup. Now set it up first before you start doing any further computation. Now, once you're done with that, those computations, then you can focus on the structure, right? Hypothesis. Null hypothesis, alternate hypothesis. P1 Thomas passing rate is less than Mr. Huang's passing rate. But you just say it in the nicer way. See, to say Mr. Huang's passing rate is higher than Thomas has the same meaning to saying Thomas' passing rate is less than Mr. Huang's. But when you say Mr. Huang passing rate is higher than, even though the same meaning with the second sentence, it sounds better. Okay. To say that I am younger than you sounds much better compared to you are older than me, especially if you are a woman, I heard. Okay. When I say to a lady that, oh, you are older than me, it sounds offensive. But when I say, oh, I'm younger than you, sounds humble. Okay. Even though those two sentences has the same meaning, but the way I say it can make it offensive. Okay. And I may don't have that in mind, but I can understand if somebody said, Thomas, that's rude. Okay. When I first came to America, I didn't think that way though. I actually learned from my pastor's wife that it's one thing about what you say, it's another thing about how you say it. So Thomas, you need to learn to say it right. Not only say the right thing, but to say it in the right way. Okay? It's like a silver apple on the golden plate. That's how she said it. And I believe that's a quote from the Bible. From the Bible. Okay, so this is the claim, and that is left hand. Huh. Okay, let me modify that. So the modification will make it null hypothesis, alternate hypothesis, P1 minus P2 greater or equal to 0, P1 minus P2 less than 0. The same to what we did in the previous two hypothesis testing on two parameters. Step 3, test statistic. This is the painful one. Okay, Z is equal to P1, that's P1 hat 0.33333 minus P2 hat 0.47059 minus P1 minus P2, that's minus 0. That's the constant on the null hypothesis, over square root of, this is the painful one. So painful. 0.41379, that's P bar times Q bar 0.58621 over the sample size of the first one is 12 plus copy paste the same thing. So I need to extend the line over here. 0.41379 times 0.58621 over 17. Now, how to use calculator? I will show you first how to use calculator to compute this. That's parentheses 0.33333 minus 0.47059 minus 0, right? But it's nothing divided by the square root of 0.41379 times 0.58621 over 12 plus. So I'm barely done with the one here. Now I will proceed with this part. Okay, plus 41379 times 0.58621 over 17. Wow, that's a lot, huh? Boom. That's negative 0.58383. 8383. That's a small number. Huh. Okay. And step 4, p value. That's a left tail test, right? C score is on the left hand side because it's negative. So my p value is normal CDF. Let me find the area here. Normal CDF, negative E99, negative 0.5838301. It's normal CDF, oops, normal CDF, negative E99, the upper one is negative 0.58383. 27967, 0.27967. Then step 5, step 6, I think you can do it already. I will show you now how to use your calculator to do so. You will go to Test, to Proportion C-test. You will see every time you deal with proportion, it's C-test. To Proportion C-test. Okay. What is X1? So I actually start from the raw data, and calculator will compute everything for us. Cross this first. X1 is 4, N1 is 12, X2 is 8, N2 is 17. Oh, by the way, from here, can you see that the number of students passing Mr. Huang's class is twice the number of students pass Thomas' class? Notice if I say it that way, sounds like Mr. Huang is very good, and Thomas is really bad. I mean, Thomas is bad, right? But saying it in this way makes Mr. Huang is really good. Oh, you know what? The number of people passing Mr. Huang's class is twice Thomas passing, right? But then when we do the hypothesis testing, hold on, less than, yeah. Less than P1 is less than P2. Calculate. This is what I get, screenshot. And put it here. Notice that my P1 hat is this. My P2 hat is this, but this is our P bar. This is our P bar. Now, our calculator cannot write P bar, they use P hat, but this is our P bar. Okay, now, the thing is, how about the C-score? Oh, the C-score is different, huh? The C-score is different. Seems like it's actually quite far different though. It's not a little bit different. This is quite far different. Did I punch anything wrong? Let's check my computation. Let's check my computation. Here that parentheses 0.33333. Now, I do expect there will be something different because I already have rounded error here, right? But I didn't expect that difference to be more than 0.2 points higher. But it is possible. It is possible. That's why don't do rounding. 5 decimal place rounding, especially for proportion, is appropriate. 0.58621 over 12 plus 0.41379 times 0.58621 over 17. I believe I punched something wrong. So no, not this one. This is 73717. It's negative 0.73717. 917. 917, not 717. So it's 917. You see that it's slightly off from what the C-score they have. Slightly off. But I do expect that there will be some difference. I do expect there will be some difference. But the difference that I have earlier was too bad. Okay, so I need to change this also. I need to change this also. This will be negative 0.73917. Okay. Now the p-value we get should be, you know what? Instead of crossing it over, I mark it wrong. The p-value we get will be from here. This is the p-value. This is our p-value. Okay. That's our p-value. Supposedly, but let's see if I do it by hand. Normal CDF. And this is negative 0.73917. 22990. So that's 0.22990. So a little bit off, huh? Off at the ones. Off at the ones. A little bit off. But yeah, we still have the same conclusion, right? We still have the same conclusion, that is informal conclusion, fail to reject null hypothesis. And then step 6 conclusion. Is the alpha. I think I used 3%. Okay. At 3% significance level, there is insufficient evidence to support the claim that Mr. Huang's passing rate is higher than Thomas. Notice that we does not say that's wrong. We did not say Mr. Huang's passing rate is not higher than Thomas. That's not what we are saying. We simply say there's not enough evidence. But Thomas, we have evidence. Yeah, you have evidence, but that's not enough. That's not enough. Your evidence is not strong enough. in the Court of Justice, they have something called preponderance of what? I forgot what's the term. Preponderance of evidence. So based on the evidences they saw, then they make decision, and those evidences are circumstantial evidence. So from the circumstantial evidence, is that enough to claim somebody, for example, is corrupted? Okay, if from the circumstantial evidence is not enough, then they don't need to find substantial evidence. Okay, because even circumstantial evidence is not there, there's no then they don't look for substantial evidence. Okay, now I have a couple minutes left. Let me do one problem super fast, but I will get this from give me a sec. I will get this from a problem from my handout, but I promise you I will make it super fast. I will not do the whole. I will not do the whole 6 steps, but I get you how to use calculator, and then you fill in the details yourself. Okay, let's say from the handout I will use problem number 12. Stony Brook University Applied Math and Statistics. From 161 people visited one hospital's emergency room in a 6-month study period with injuries from inline skating. It is found that 53 people using wrist guard, and 6 of them had wrist injury. Now those without wrist guard, (108) of them didn't wear wrist guards yet. 45 of them have wrist injury. The question is, does wrist guard reduce wrist injury? So we want to show that the first group proportion is less than the second group proportion. Okay, that will then be the alternate hypothesis. Right, now let's get all those numbers. I go to stats, test, 2 proportion C test, then x1 is 6, x2 and 1 is 53, x2 is 45, n2 is 108. And we want to test if P1 less than P2, calculate. So then from there we get, let me use green color. P1 hat will be 0.11321. P2 hat is 0.41667. P bar will be 0.31677. Now, in your test next week, you need to show me step 1, 2, 3, 4, 5, 6, including the formulas, including the work. But at least from your calculator, after you say, for example, after you say test step 3, test statistic. I still want you to write the formula down. Okay? I still want you to write 0.11321 minus 0.41667 over square root of 0.31677 times 0.68323 over sample size for the first one is what? 53 plus 0.31677 times 0.68323. This guy coming from 1 minus this guy. Okay, they should add up to 1. Sample size for the second is 108. Okay, you still need to write it, but then for the C-score, you just quote from above, negative 3.88939. And then the p-value that's negative 3.88939. You will say, oh, p-value is equal to normal CDF. So you pretend that you use calculator to compute it, right? This tells me you know what to do. And you know how to do it fast. The p-value is 5 blah 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 e to the negative 5. Don't forget this part. Okay, especially this part. Don't forget that. And that will be e to the negative 5, right? So 0.00005 something. And step 5, step 6. Okay, blah blah blah. Step 2, don't forget. At the end here, you need to have P1 minus P2 minus 0. Okay? Yeah, that's basically the structure and therefore the computation and the calculator work. I will end here. Next week, your tests will start from 8 o'clock.